Good afternoon, ladies and gentlemen. My name is Michal Šprlák, and I came from the University of West Bohemia in Pilsen to show you what we have been working on together with my colleagues Pavel Novák, Martin Pitoňák, and Eliška Hamáčková. To be specific, we have been working on the spherical harmonic analysis of the third-order gravitational tensor and its implications for a future satellite mission. I will start directly with a motivation. We know very well that several satellite missions have been under consideration in the quest for an accurate static gravitational field determination. One of them could be measuring the third-order potential derivatives. As compared to the second-order derivatives, these are sensitive to the higher frequencies of the gravitational field. Moreover, the third-order potential derivatives are not influenced by rotations of moving platforms. Another supporting fact is that sensors for observing the third-order potential derivatives have already been developed. This may be documented by the terrestrial experiments Dulkin and Magia devoted to fundamental physics. Also, a satellite mission that would observe the third-order potential derivatives was proposed. It was originally titled Optima, and its continuation is ongoing within the GeoQ project. However, there are several open questions regarding the satellite mission measuring the third-order potential derivatives. For example, some theoretical properties, spherical harmonic analysis from such observables, error propagation, required instrumental noise, or possible impact on gravitational field modeling. We have been dealing with these questions, and I will briefly show you what came out. Let's now discuss theoretical issues. I will begin with some basic properties of the third-order gravitational tensor. Generally, in a three-dimensional space, this tensor is composed of 27 components and may be visualized as a cube. We will assume that these components are related to the local north-oriented reference frame. At the first sight, things look complicated and we can see this mess. However, if the gravitational field is continuous, the tensor components are symmetric with respect to the pairs of indices, and we are left with 10 components describing the tensor completely. Another simplification comes in a mass-free space. Here, three Laplace equations hold, reducing the number of independent components to 7. So, there is no reason for any panic when working with the third-order gravitational tensor. Rather than working with the individual components, it is reasonable to divide them into 4 groups. These differ according to the number of the vertical and horizontal indices. Namely, we have 1 purely vertical component, 2 vertical horizontal components, 3 vertical horizontal components, and 4 purely horizontal components. Important property is that we can find an orthogonal basis on the sphere for each group. This pushes us one step further to the spherical harmonic analysis. There are many approaches for the spherical harmonic analysis, and we opted for integral formulas. The simplest one considers the purely vertical component. We simply multiply it with the spherical harmonic function of degree n and order m, and integrate over the sphere at altitude h. To get the correct spherical harmonic coefficient, we multiply the result of integration with the corresponding eigenvalue and constants. I will not show you the other three integral formulas, but you can imagine that these get more complex with more horizontal indices involved. Some combinations of the third order potential derivatives would appear under the integral, and also the spherical harmonic functions would be differentiated with respect to the angular spherical coordinates. If you are interested in some error estimates, you can derive simple analytic error models. Let us assume that we have independent measurements of the 10 components performed with the same precision. Also assume a constant altitude h and an equal data density distribution specified by the mission duration d. Moreover, the satellite orbit is polar with negligible uncertainty. Under these assumptions, we can obtain a simple analytic formula for the average error degree variances defined by several parameters, namely the accelerometer noise power spectrum density, satellite altitude, mission duration, and spherical harmonic degree. As you can see from the eigenvalue, this formula corresponds to the spherical harmonic analysis of the purely vertical component. For the other integral formulas, we may get similar error models, values of which differ only by integer multiples. The noise level for the purely vertical component is the same as for the vertical horizontal components. However, the vertical horizontal and the purely horizontal components perform worse by 3 and 10 times respectively. With the integral formulas and the analytic error models in hand, we can perform some numerical experiments. We investigated two questions. In the first one, we were looking for the required noise level of an instrument observing the third order potential derivatives. We chose a reference solution that corresponds to observations of the DZZ component with the noise power spectrum density of 10 millietvech over square root of hertz, altitude 250 kilometers, and mission duration of 2 months. The corresponding performance is depicted by the red line and nicely agrees with the first release of Gauss global gravitational field models, especially for degrees greater than 100 and intersecting the signal curve at degree 208. For the same altitude and mission duration, we found a curve for the third order vertical derivative VZZZ, which intersects the signal exactly at the same degree 208. This curve is depicted in blue. You can see the flatter error spectrum for the third order component. The table summarizes what is required from the accelerometers if we use the differential accelerometry. If the separation is 50 centimeters, the accelerometer precision is at the 10 to minus 17 level. This is 5 orders less than for the Gauss mission. For larger separations, the performance is less demanding. If we had 10 to minus 12 accelerometer precision noise level, the separation would be 87.5 meters and 27.7 meters for the 10 to minus 13 instrumental noise level. So far, we investigated only the case with the satellite at altitude of 250 kilometers and the gravitational field to degree 208. our next task was to look at a broader picture. Imagine that you launch a satellite mission with duration of 2 months that carries accelerometers separated by 50 centimeters. Consider altitudes from 0 to 500 kilometers and the spherical harmonic degree from 2 to 360. For every h and n, we found the required accelerometer precision such that the signal to noise ratio was 1. The related equations are presented on the slide for VZZ and VZZZ. You can certainly recognize the Cauchy rule together with the analytic error model presented before. Let us look at the resulting figure. The order of magnitude for the accelerometer noise power spectrum density is shown as a function of h and n. The figure contains lots of information. For example, if you want to determine the spherical harmonic coefficients up to degree 200, you can read the altitude and the accelerometer's noise. Or, if the altitude is fixed, say at 200 kilometers, you can read of the maximum spherical harmonic degree for a given accelerometer's noise. You can also see the difference when applying differential accelerometry for measuring the second and third order vertical components. Clearly, the red and blue curves are very close, above degree 200, and they are shifted by 5 orders of magnitude. Therefore, to get the spherical harmonic coefficients up to the same degree, second-order potential derivatives require less precise accelerometers. Let's now go to the conclusions. In this presentation, we have discussed a satellite mission which would eventually observe the third-order potential derivatives on board. In this context, we derived spherical harmonic formulas and the corresponding analytic error models. We have seen that the integral formulas with the vertical and vertical horizontal components should be preferred. We have also seen that the accelerometer noise level should be at the level of 10 to minus 17 to get the gravitational field similar to that from GOES. This is obviously beyond the current technological limits. Overall, observing the third-order potential derivatives is highly demanding and puts a question mark on thinking about such satellite mission. However, I will not give a definite no until someone else proves it independently. This is all from my side, and I would like to thank you for your attention.